Hi everyone, so great pleasure having you there from IIT Indore. And we're going to discuss at a freelancer on trade theory, which is very kind of make a thanks for
I cannot promise pedagogy, but okay, let's see. So thanks for the introduction and thanks for inviting to give these talks. So I'm going to talk about string field theory, but I must confess I've not thought about like string field theory for the past few years. Only recently, like I have started thinking since I'm working on some problem, but okay. I won't be able to talk about that in this set of talks. But, so let's see. So let me begin with some motivation. It will be some extended motivation. And I will be assuming the first quantile. You are familiar with the first quantile string theory. At least you have basic idea about what happens. Okay. So what happens? Let me just state. I am going to just state some facts in these slides. So in the usual first quantile string theory, we deal with a single string, which is propagating through space-time. And so we quantize this single string, and the main player in this approach is the two-dimensional conformal world-shape theory. And for many purposes, such as dealing with IR divergences, or suppose you want to have RR background field, like you want to define ADS, this first quantized framework is not very helpful and not very convenient. To see like these problems in a little more detail, let's recall some aspect of this conventional string perturbation theory, which is based on this worldsheet approach. So this is the Polchanski level string theory. So in the standard worldsheet approach, the G-loop amplitude is computed by doing an integration over the moduli space of the genus G Riemann surfaces. Okay, and more specifically, suppose you want to compute some endpoint string amplitude. So what do? Is you consider first of all some correlator, some correlation function. So these VIs, say V1 to Vn, represent the input information about your string states, and they are vertex operators. So you compute this correlation function on a genus G Riemann surface with n functions, and then you integrate over the moduli space of this Riemann surface, genus G Riemann surface with n external states. Okay, and this Mi parameterize the coordinates on the moduli space. So this is the general structure of amplitude you have. And one of the most important ingredient of this approach is the conformal invariance of the worldsheet theory. So basically, one aspect of this conformal invariance is that it dictates that the vertex operator representing these external string state should be primary operator of conformal weight 1, 1. And this in turn implies that on-shell condition for the so basically, if you demand, so conformal weight of a vertex operator is given by, so your vertex operator has some factor e to the power ik dot x, and that has its weight involves some k square, alpha prime some k square by 4, and then there are some modes coming from this del x. And so if you demand that total conformal weight to be 1, 1, then you get basically this condition, okay, where m is fixed. So so basically conformal invariance requires that this on-shell condition must hold to all loop orders in the perturbation theory. So this means that the mass of the state is fixed once and for all, and any change in it destroys the conformal invariance of the worldsheet theory. Another constant which is imposed by the conformal invariance is on the classical equation of motion of the space-time metric. So the conformal invariance of this worldsheet sigma model. So if you consider the one loop like amplitude and demand that the theory should have the conformal invariance at one loop, then you have to set a beta function computed on this genus 1 surface to 0, and that in turn gives you this Einstein equation for the this metric tensor, some generalized Einstein equation. And only the backgrounds which correspond to vanishing of these beta functions are consistent by and violating this condition all results into the breakdown of the worldsheet theory, and the usual machinery of this standard string perturbation theory do not matter. But there are like many instances where you might want to like relax like this condition. So for example, so these conditions are both of these conditions this equation of motion and this on shell condition, both are classical conditions from the space-time point of view. But any classical quantity, unless protected by some symmetry, it must change when we take quantum effects into account. And in general, you can compute the corrections coming from G string.
This Einstein equation which you get is only valid for one loop calculations or even in higher loop.
So I think at one loop you get this higher loop. Okay, I'm not sure whether this has been computed. Maybe Shiraz, you know.
Einstein equations are obtained from beta function.
Yeah.
So in some sense, it's trivial. Right? I mean, from the point of view of string perturbation theory, it's trivial. And then since it's a local condition, as Mritunjay just saying, you would put that same conformity theory both on a one loop, then on a two loop, then on a three loop, genus one, genus two, genus three. But his point is that the computation of the Einstein equation was just a beta function classical computation, and you're using that background to do a high loop time. It should be inconsistent.
Right. I guess if you consider this more alpha prime corrections, then you will get all these supergravity equations.
But let's count all of those, as I call those Einstein
equations.
Yes. For the point you're making, let's say you've done that exactly. So you've got an exact sigma. So an exact sigma model on the well sheet is an exact classical solution.
Yes.
But now if you do a 3-loop calculation around a classical solution to Einstein equation, without accounting for the quantum correction, the fact that this solution itself gets corrected at something, you should get into trouble.
Yeah.
And it's very clear, as he said, from the point of the on-shell particles. Then it's very clear. Because if you compute an S matrix using the wrong mass share condition, you're going to get into trouble.
Right. So the standard worldsheet theory is not equipped to incorporate these quantum effects. So basically the corrections coming from the G string when you consider the hard genus surface. In particular, if we impose these classical conditions, namely fixed mass and fixed space-time background at loop level, then they result in some unwanted divergences in the worldsheet perturbation theory. And let's see, more precisely, let's see what happens. So let's review some of these familiar divergences which appear in this worldsheet string perturbation theory. So let's consider the simplest scattering calculation, the scattering of 4 closed string tachyons in bosonic string theory. So this you can show. So they are described by this Koba-Nielsen integral. So here Zi represent so when you compute this 4-point closed string amplitude, so you have to insert four these punctures on the Riemann sphere. So 3 of these you can fix using the SL2C symmetry of the Riemann sphere, and one of the puncture, its location is not fixed. So here you have integration over that location. Ki represent the momenta of the these string states. Okay, so you have this integral, but this integral diverges in the regime. Suppose you have this alpha prime k dot ki, which is the exponent of this factor z minus zi. So when it is less than -2, then this expression will diverge when this integration variable z goes close to this one of these zi. So when unfixed puncture collides with this one of any of the fixed punctures. Okay, but this is a regime which is a physical regime. Okay, in this regime they correspond to some interchange of some propagation of some intermediate state, which is like a physical regime. So you really want to know the answer for this in this regime. And naively, we cannot compute this amplitude for arbitrary value of the external momentum since it diverges. So in the usual approach, what we do is we get around this issue by doing some analytic continuation. So we first consider the kinematic regime in which the integration over so integration over z is well defined. So you consider alpha prime k dot ki greater than say this -2.
So
So-
this would also diverge when it's less than zero, right?
Yeah, less than zero.
No, it would be an integral singularity. It's, sorry. Dx by x to the power alpha.
Oh,
Yeah.
It only diverges when alpha is greater than. The d2z is z dz r dr.
So what you do is you first consider the kinematic regime in which the integration over z is well defined. Okay. So in that case, the integration over z can be performed, and the result you have the standard result of this Virasoro-Shapiro formula. Okay, and this is perfectly well defined expression. And this expression can also be used for this kinematic regime in the original, in which original integral was like divergent. And we define the amplitude in the original divergent regime by this expression. But this type of analytic continuation is not always possible. And because, I mean, one reason is because in general, there does not always exist an analytic expression for, suppose you are considering loop amplitude, this was tree amplitude. You are considering, suppose, loop amplitude. Then in principle, we don't even have an analytic expression in any kinematic regime. Due to this, we cannot use this kind of trick to get the formula. And apart from this analytic continuation issue, this amplitude has another more serious problem. This still will have pole when the gamma function in a numerator they vanish. They correspond to some physical singularity. Okay, they are real S-matrix singularity. And from the quantum field theory point of view, these divergences are easy to explain. So, for example, if in a quantum field theory, if you have a Feynman diagram like this, then if suppose you have this propagator, which is given by 1 by k square plus m square, when it goes on shell, then this diverges. So we have this issue. Let's now move to the loop amplitude.
So what was the last issue?
Sorry, which issue?
This last one has poles when they were in the.
Oh, this one.
No, whenever the gamma functions.
Yeah, whenever this gamma, whenever you have zeros of this gamma function in the numerator, then of course this diverges. But these are more
Zeros, then you should just have.
gamma function diverge. I mean, the gamma
Argument goes to
Argument.
Yeah.
to negative.
When the.
So when-
functions in the
No,
numerator
so
have
when
poles.
the argument of this gamma function vanishes,
So, but I also didn't understand. So, why was it a problem?
no, so it's okay. It's not problem at this step for the tree level. It's just its interpretation is just that okay, you have some on-shell particle
Yeah.
that's propagating. That's it. But this becomes problem when we go to the loop. So at say at one loop, the 4-point function is given by this torus topology.
You said something that I didn't know. You said that there are loop amplitudes for which the analytic continuation never works.
Okay. Loop amplitude. Okay, so yeah, so basically there is this prescription by Witten, where you can use this some contour prescription to define on-shell integration over this on-shell moduli this thing. So, but that prescription has not really been really used. I mean, to define the loop amplitude in okay. So there are some papers by Mizera where they considered this at one loop using this some kind of. They try to describe some kind of this. They try to give some this contour prescription, but how exactly it works at all loop order is not very clear. I mean, how you so it's a more a problem of calculation. In principle, one expects that string field theory should be equal to some kind of contour prescription. But okay, string field theory gives us more mileage. But still, I mean, if you want to define the this contour integral, okay, there is okay, one could try to give some prescription in this complexified moduli.
I think it's not been done.
It has not been done. So at one loop, say consider this torus diagram, and for 4-point function, you have to insert these 4 functions, and the CFT correlation function which needs to be integrated over this moduli space of torus is well defined in this case. Okay, but the problem arises when we try to perform the integration over the moduli space. what happens is the integration over moduli space contains region in which this Riemann surface degenerates. So in particular, for example, there will be region in moduli space where torus degenerates like this. Okay, so where you have a situation where say three puncture come close to each other and one puncture is like separated from these three by a long handle. And similarly, you can have a situation where these four punctures are like together and then this hole is like separated by this long tube. So in the standard worldsheet theory, there is no systematic way to deal with like these kind of divergences. Okay, modulo this contour prescription.
So just going to the last one, that torus there is like correction to the vacuum inlet.
Yes.
Which we expect in the supersymmetric theory just to be zero.
Yeah.
So, why isn't that just zero?
Which one?
The last.
This one.
Yes.
Okay. So in general, it can still contribute to your. So basically, what it does is it contributes to the shifting of vacuum. Okay, I am coming to this point very shortly.
So, just to say, I would have thought that roughly this is like a source.
Source.
This long tube
Yeah.
and then a source. The source is like cosmological constant.
Uh-huh.
Right?
Mhm.
So in theories, when there's a cosmological constant, that
Yeah.
should have been a problem. In theories, when there's no cosmological constant, should not have been.
Should not. Yes. So to get, intuition about like these divergences, it's useful to get consider.
I just coming back, but similarly, you'll probably come to this, but just to, okay. Again, the left diagram, if I had, let's say, the cross on the left hand side was a graviton vertex.
Yes.
Then once again, I would have thought naively that
Okay,
I do
because
feel
one for graviton it will not be.
it will not be.
Will not
It's
be.
for some massive constraints.
Yes.
Nice.
So let's consider a quantum field theory, and let's consider this massless phi cube theory for this one. So at one loop, some of the divergent diagrams which we encounter in say phi cube theory are these. We have. So in QFT we have divergences which come from this integration over the loop momenta. In string theory we don't have to worry about these divergences coming from these loop momenta. Once you restrict to fundamental domain of this moduli space. But these diagrams also diverge when the internal propagator connected to the loop goes on. So for the first diagram, this will happen when say 1 by k square plus m naught square goes to infinity for like this propagator. M naught is suppose it's a classical mass of the external state. So what is the remedy in quantum field theory? So remedy is this diagram is not supposed to be treated in isolation. We have to consider all possible insertions on the external level. Okay, so you have to consider one loop, two loop, all loops, all possible insertions, and this leads to the concept of mass renormalization. So more specifically, for two external lines, we rearrange the diagram. So suppose you have 2-point function, then you rearrange all possible 2-point function in this way. So you consider 1 pi diagram, and then glue all these 1 pi diagrams in this way, and this gives mathematically you can write in this way. Say propagator is 1 by k square plus m naught square. Then you have 1 by k square plus m naught square. Say sigma is the value of this 1 pi part, and then this. So you have this infinite series, and this infinite series can be summed formally. And what we do is we look for the pole of this 2-point function, and which in turn leads to a condition of this type, k square plus m naught square plus delta m square equal to 0. And what it shows is that m naught square plus delta m square should be the correct mass, which takes into account the quantum effects. And if we use this value of mass for our calculation, then we don't encounter this sort of divergences. So for computing loop diagram, we should use this renormalized mass instead of the classical mass m naught. So what is the important lesson we learn from this example is that if we do not take into account the quantum correction to the mass of the particle, it leads to divergence. And in quantum field theory, a well-defined way to take into account this quantum correction, it requires dividing the diagram into 1 pi and 1 pr parts. So this is the way quantum field theory handles these sort of divergences. And in the standard worldsheet approach of string theory, due to the insistence on the conformal invariance, it is very difficult to modify this classical on-shell condition. And moreover, these string loop amplitudes are given by a single diagram. Like you have a single diagram, and there is no way to divide this diagram into one PI and one PR part. Okay. And at the one loop level, this torus degeneration, where you have one puncture separated from these three punctures, corresponds precisely to this sort of problem.
So how is the problem of OKT manifested in the model space integrals?
So basically, you have okay. So suppose you are doing some Schwinger like parameterization, then you will see that this Schwinger parameter goes to like infinity.
So you're saying if I just were to do this kind of I know the modular space, presumably it's a compact modular space, and I want to do this integral.
Right.
Potentially, I can put it on the computer and do it. That will not be successful. What goes
Okay,
wrong?
so to like even for doing this on computer, you need to know. Okay, you need to do some kind of some decomposition of moduli spaces.
Why? I mean, it's some modular space, right? I mean,
Yes.
torus with 4
Yeah.
points, it's some modular space.
Right.
You get the divergence.
You will still have divergence.
You get the divergence.
And one can trace it to this limit.
This.
Yeah. It's like you said in the quantum field theory.
Yeah.
That,
Yeah, but so a particular corner of the modular space.
This-
you will see this.
Yeah.
This so yeah, I mean,
Explicit.
so basically, I mean, if you write in like some Schwinger parameter representation, say for one loop it can be explicitly done, then you can explicitly see it.
Can you fill the second point?
At this one.
Yeah.
So basically, so here we had like this kind in QFT we had this kind of like that. There was a like loop on the external like this line. So this particular like region of moduli space where you have three puncture on one side and this other puncture along with this loop part is like separated by this long tube. So this particular region corresponds precisely to this kind of like divergence.
Because of this S square plus n square into infinity.
Infinity, I mean, yes. So if you try to compute like this thing.
in a string worldsheet theory, automatically strips off external. Meaning LSZ prescription says you go computer correlation function and you strip off the external ones. The string worldsheet perturbation theory does that. But that external thing is not. But now by doing this, you've got like an internal problem. So that long tube has all states, including the state that what's
Massless. Okay.
now since that guy is forced to be on shell, that internal propagator will go like the same. Because 1 over k squared plus n squared, where k squared plus n squared is same. Okay, so that internal propagator there will go to zero. Technically, right? Right, so even though the formalism was clever enough to strip off the external propagator, it of course can't strip off internal propagations. They're part of the thing. And that will go to zero because you don't have the maneuverability to go off shell.
Because of the conformality.
Yeah.
But that was there at 0 to 7, right? Not just tourist.
Yeah, it will be present for all genes.
But there's no diagram like this at zero.
Yeah.
You wonder it. Like at zero loop level, this is something coming in, something happening. And you've already stripped off the external block. The formalism has stripped that. You're doing LSZ, sir. Now you need something happening, you need a mask. What he's doing here is like a 1 pi mask correction line. You need a loop. If you go back to your field theory diagram,
Yeah.
that bubble there was that. You need that.
So let's consider the second diagram of phi cube theory. And this one is known as the famous this tadpole diagram. And by momentum conservation, you can easily see that the momentum flowing through this internal propagator, which is connected to the loop, it must be zero. So hence, if you have a massless field, then we again get the divergence. Okay? If we try to compute naively like this one. So what is the interpretation? And there is a standard interpretation of this kind of tadpole divergences in quantum field theory. But these kind of divergences arise if there is a quantum correction to one point function. And this basically means that your classical vacuum around which you are like doing your quantum field theory, around doing perturbation theory, that is no longer the vacuum of the theory. Okay? And in quantum field theory, there is a standard way to cure this kind of problems. Yes.
So the same kind of divergence around the cosmological constant, you can cure even without this, right? Because you can just modify. So they have the problem with conformity where it doesn't arise, but you're saying there are divergences with respect to the expectation and things like that. You can't modify the covering the rule.
Say what you said, linear cosmological field.
So if you have a cosmological constant based divergence, then I think Pulsicki also says that we can just modify like the cosmological constant and then have a different value of the tree diagram with the top. Right.
But how do you modify that in string theory?
Yeah.
I mean, if you're doing effective field theory, that loop would be changing the cosmological constant. Absolutely right. But in string theory, you're working around flat space. Let's say you're doing SO32 heterotic. I mean, one of these non-supersymmetric heterotic theories, where there would be a one-loop cosmological constant. Then this would be just, how would you deal with the equations?
I thought the idea was that the divergence would have the form of like the previous states, like the S2 diagram, but with a different. You can't.
You're saying absorb that into changing the sigma mode?
Yeah.
But there's no systematic way to do that. You're saying Fisher's asking.
No, not systematic. I mean, like just for the cosmological constant, I thought since you could work with any value of the cosmological constant.
So you're talking about string one-sheet constant?
No.
I think you are. Space-time cosmological constant changes your sigma.
Yeah, I thought it's not changing sigma.
Sigma mode will be a different metric. Like, I'm now saying, how do you do it?
Okay.
So in quantum field theory,
In
what
supersymmetric theory, this is not an issue.
in supersymmetric theory, yeah, I mean, whenever of course, if your like cosmological constant vanishes, okay, then it's not a problem.
Which in particular?
Yeah.
Like, so it would not, type 2D flat space would not.
Yeah,
I think the diagram,
I mean, if I want to, if I actually try to compute this particular.
Maybe in some, probably in
single
some cases you will get the zero, but
will I get infinity?
sorry.
In supersymmetric cases, will I get zero because it's a delicate thing, right? It's infinity times zero. So whether the cancellation happens first or whether the divergence.
So if one could really compute like this in string theory, then okay, we could see this. But how exactly you like even approach to compute this is not like very clear in this like worldsheet approach.
The other thing is that you have the NS sector and R sector. And you have to combine them all to get this.
Yeah.
Individually, they are not supersymmetric.
They're not supersymmetric. Yeah.
Specifically for the cosmological constant, it's the absolute set.
So you get infinity. You will have to be.
Then you'll have to infinity minus infinity.
Something. Yeah. I mean, if you could compute, okay. Then.
Sorry, it was a cosmological constant, you get zero. That's the absolute set entity or something. They just cancel.
They cancel out just for one. But
Yeah,
that's probably. But that's what happens, some more spin structures.
Yeah.
But suppose we're doing spin structure by spin structure. You read this diagram. Spin structure by spin
You have
structure.
to do the integral with a particular sector, right?
Okay, saying is if you do integral first, you get infinity.
Yeah. So then you will get infinity minus infinity. And maybe then you can use some prescription to make it that. But how do you find it?
But I don't know where could they spin structure. I mean, you to torus with two insertions, I can look at it, right? I can look at that problem. Torus with two insertions. And then the particle that is propagating in the middle, it's not like on the torus what bounded condition.
Yeah, yeah. You're doing a one loop partition function.
Yeah,
You have to sum over all the
okay.
So what you do in like quantum field theory to like
It's some Green-Schwartz type thing.
Yeah.
If you use that kind of philosophy, you get around this.
Mm.
Right? So something that keeps the supersymmetry more manifest.
But yeah, I mean, but this kind of like divergence where all the punctures come together and then it will be present in a hard genus also. Then how do you exactly like deal? I mean, okay, you have to.
And for instance, in let's say one of these non-supersymmetric heterotic theories,
Yeah.
clearly it's a matter of principle.
So in QFT, what you do is you consider this.
Sorry to interrupt again, but is there like a canonical order in which you do you like compute the partition function and somehow instructions some specific moduli space parameter then integrate, or is there a canonical order which you do in the operation?
Oh, you mean like first you sum or first you do first? Yeah, first you sum.
Yeah.
So, okay, maybe you could have this.
So which is it like
I mean, say first sum, then integrate, we will have this.
so that's the right order.
So what you do in like what you
That will be the right order because you preserve a bunch of traits. You preserve that, the supersonic. You'll see the
I
supersonic.
think because you do it for a single conformity theory, so for a single conformity theory, so some.
So you consider this 1pi effective potential, and this will have a leading contribution which comes from the action, namely this lambda by 3 phi p. It comes from action. But this one loop tadpole diagram implies that the effective potential will get a one loop quantum correction, say lambda by 3 phi q minus c phi, where c is some constant. And one can now look for a local minima of this, which is at say phi equal to is per c by lambda. And then if you do the perturbation theory, your QFT around this new minima, then you will not have this tadpole divergence. So the 1 point function computed around this new vacuum will vanish. So the important lesson we learn from this example is that if we do not take into account quantum correction to the vacuum of the theory, modulo all the subtlety, then it leads to divergences in the loop amplitude. And the way to cure this divergence is to work with the shifted vacuum. And in string theory, this tadpole divergences show up in this kind of degeneration of and the analog of this original vacuum, phi equal to 0 in string theory corresponds to
So your model was chosen so that the field, that if you can go back one.
this one.
This one, yeah. So the field is massless,
Yeah.
but not exactly flat.
Yes.
If it was massive, there would be no problem, presumably. And if it was exactly flat, there would be a problem no matter what, even in what we think.
Right.
It would change to a time-dependent background or something.
So this analog of original vacuum basically corresponds to the conformal invariance of our worldsheet theory. And modifying this vacuum destroys the conformal invariance. And moreover, it is not easy to isolate from the full amplitude precisely the part which is responsible for the tadpole divergences. So QFT techniques, we cannot really make use of them in the standard worldsheet approach. But it turns out that string field theory can systematically handle all these problems. And since it is a field theory, we can borrow all the usual techniques of field theory to cure these IIT. And so to see what is involved in developing a field theory of strings, first recall that the physical string states are defined as an element of this two-dimensional BRST homology. So suppose QD is your worldsheet.
Will this be your main motivation?
Okay, so there are like various one motivation is RR like background, and there are other things, but I'm not going to get too much into the motivation and the application. My main focus will be the formalism. So it was just the way, it was just a way to like motivate why we are
It's a great motivation. But one thing I noticed, don't say, just to understand your perspective, is you did not say non-perturbative.
Yeah. So
formulation.
non-perturbative, of course. There is of course a non-perturbative formulation also, like all this tachyon condensation and.
No, but do you, in your view, is string field theory moving towards getting a non-perturbative formulation of string theory, or is it just some improvement of string perturbation?
I think at least there is one calculation where it has it has shown that it has it can handle this non-perturbative.
Non-perturbative meant they're classical, but not your tachyon condensation. Those were classical.
Right.
Okay, so it was like doing classical fields, but not exactly non-perturbative. That's right, because it was large in field space, but not in G string.
Right.
I meant G string.
Yeah.
Is your view that once we write down this Lagrangian and quantize it, and if you have a humongous computer that defines everything, or is it?
So right now, it seems things which I have seen so far, it looks at least currently it is like a more organized way, systematic way of doing the string perturbation theory. That's for sure. But how much mileage it can give, it's like, okay, for example, this RR calculation, taking into account the RR fluxes.
Which would
So
also
now-
be great, but that would also be in string quantization theory better.
Yeah, right. But I mean, in this approach, in the worksheet approach, it's not even clear how you define. I mean,
Nobody is questioning, at least I'm not questioning that it's useful, it sounds fantastic.
Right.
But I just want, sometimes I hear people say
Yeah.
that they think string field theory
Is the non-
is going towards non-perturbable string theory. Nothing in what you have said is fantastic.
The current developments are kind of towards more like this.
perturbation.
What I
Yes,
showed.
yes. Yeah, yes. So,
Yeah.
I mean, yeah, non-perturbative. I mean, so for example, one calculation which, for example, we would like to see, say, analyze say dualities, using this say open-closed string field theory and so on. If it could give some insight, but okay, I have not seen. I mean, anyone has analyzed so far. So, but it's
Just one last thing, and I'll shut up. If you put string field theory, whatever it means, on ADS 5 times, that's fine. Say you manage to understand Raman fluxes or whatever, you manage to do that. Would it, in your view, would it be in principle equivalent to full n equals for n?
I think so.
So we'll see all the gluons,
I think so. We should.
we'll see the stringy exclusion principle. We'll see that. Is that, can I see stringy exclusion principle constricted? That trace z to the end?
Yeah.
Is zero.
From string field theory of A, I mean,
It's certainly not than classical string.
yeah.
Right? In classical string theory, all states are independent states. So it has to somehow come out. Do you see any
Quantum.
hint for how it might come out?
Yeah, yeah.
Because it just conceptually it seems two different things could be true. A, it could be a trick to do perturbation theory better, which is already extremely useful. I'm not questioning that it's useful.
Yeah.
But
But,
B, it could be more. And I just wanted to know what you see.
So yeah, but that field stringy exclusion, would you say it's a description of non?
And that would certainly be evidence to that. Right? I mean, because that really comes from the gluons. Comes from the n cross n matrix structure. If you see that, then it feels like it is looking like it's in the gluons. Which,
When you ask this question where there is no other ones.
yeah, I suppose we can ask him maybe S3 times S3 times T form.
Yeah.
Unfortunately, where there's no RR flux, the conformity theory is a little bit single. Because there's a long strings. And cure that we need to turn on RR flux. So maybe somehow, maybe. But it's not as clean a question. This issue. But I just to say one. We know from n equals 4 that the closed strings are traces. Right? So very conceptually, what you are saying sounds to me like saying, so traces are like glue balls. And so very vaguely, it's like doing the chiral Lagrangian as compared to QCD. Yeah, because chiral Lagrangian deals with mesons. Mesons are sort of like, okay. So the kind of question we're asking is, can we recover QCD from the chiral Lagrangian? And maybe if you take the chiral Lagrangian and all irrelevant operators, in some sense, if you keep all irrelevant operators all the way, you will recover QCD. But that sounds very unnatural for us. But somehow maybe string theory is clever. Maybe it is clever enough to be the exact chiral Lagrangian for n equals 4 actions. But if that is the claim, I find it extremely exciting and I would love to see any other. Right? This is exactly what we don't usually. We don't try to do QCD from K. We do QCD from QCD. But maybe, of course, in principle, you can follow the RGM flow all the way, all the irrelevant operators, and you've got QCD. If somehow string theory is clever enough so that it's doing that for n equals 4 angles, sounds tremendously exciting. But it would be nice to see one piece of evidence.
Yeah, right now, yeah, I don't have very much comment about this. But,
They're a way to ask this question, not necessarily in the context of ADS-CFT, but just in some background that you know well. ADS-3 density or any background that may have the NSLS plus or something like that. What kind of question would be probing this question that you're asking? Or do you need this some glow on
The thing is, you don't know the right answer. Here's a context where we feel we know what the right answer is. And we feel that the theory is going to have to work very hard to get that right. Because we're going to try to create the theory of nuance from the nuance. We know that it's good. I mean, I feel this analogy of Kyle Lagrange is pretty reasonable. It's really going to be like trying to recover QCD from a Kyle Lagrange. And maybe that can be done. I mean, in principle, I think it's not an impossible thing. You keep all the irrelevant terms. But it's the kind of thing that we are taught in RG flow classes that we should. It's like trying to follow the RG flow arc.
But can we ask this, kind of more abstract? Perhaps unitarity. There's a question that can be asked using unitarity. Meaning, if you have blue balls, scatter blue balls, it will scatter into blue ones, right? But if you just consider the theory of blue balls at arbitrary high energies, it will end up being non-unitary. Meaning you will not be able to have.
All gauge variants can be observed traces. So it's not like you're missing anything by looking at it. In fact, if you take blue balls all the way, you're overcome. That's the stringy exclusion. So I don't think that you will miss intermediate states.
But very high energy states you will miss, right? Like black hole states.
No, not even those can be written as products of traces.
Yeah.
Products of traces are complete.
Yeah.
So I don't think you're missing
Yeah,
anything.
you will not miss. You will not miss.
Yeah, so what I think the key signature is this, like the kind of thing you are thinking. Kind of things are the null states. Because keeping all the traces overcomes. And the fact that you're dealing with nuance, the fact that you're dealing with n cross n matrices has these, the two things are actually the same, these null states. We will have to see some sign of these null states. And string theory is full of null states. So, but if one could see some mechanism for that would be totally fantastic. Because if somehow string theory is clever enough to produce the nuance from the blue balls, it's so unprecedented. It would be so interesting. But given how interesting it is, if the bar should be needed, one piece of news.
So I was asking that in case of ADS, like the ADS 5, we know that they are the giant gravitonic excited with ADS. So I was asking in the current formulation of the string field theory, we put deep range by hand or the string field will tell there's a deep range in the ADS.
Yeah, so when you consider this open closed string feature, then whenever you have like put in open string, which means deep ranges are there. Here.
So you are putting it by hand.
No, I mean you do just you do the string field theory for the open string, and okay, the deep ranges are there.
No, but closed string also you should be able to get solid solutions.
So basically, you mean if you are just doing the closed strings? Yeah, okay. So for closed string, you will have to put in by hand.
In the closed string field theory, at the moment, there is no bar on the momentum of gravitas. Momentum runs to infinity. Now this cutoff is at 1 by G.
What cutoff?
The exclusion is the fact that your graviton should not go larger than momentum infinity. Okay, that's 1 by G. So no particular reason that classical theory should see it.
Yeah.
But out of quantization is out of quantization of this, we will see that. That would be so interesting. Maybe it's true. Because string theory has done many material. Okay. But I would love to see it away.
Because somehow, all these questions involve, I don't know how to ask them without the RR flux, right?
I know.
And then that is the thing that we don't understand too much. So I was wondering if.
I know. Maybe we can do AS3 times C3 S3 times C4, right? That's a well understood string. Maybe you can forget about the factor. The problem?
There aren't like finite effects of permutation or before or something.
There are, yes, there are.
So would that be another?
Yeah, the one thing though is that the field theory is very poorly understood in the limit where maybe Rajesh's too. Problem there is that the field theory becomes a witch. Something in between Rajesh's. Because this is a singular limit of field theory. This is my one. Right? Because the field theory is understood as taking some well-known field theory and then doing a very large deformation. And we do the deformation to a place where we know it becomes singular. This is my one concern.
You're thinking the word shape.
I was supposed to say time, but also
It's not used in all before.
It's an orthofold when this conformity theory, though on a compact space, loses its gap because of the long strings. So many theorems about conformity theory, for instance, fail.
And this stringy excluding this case of singles, the CFT is it below this continuum threshold or below?
It's the long strings
Yeah.
are like jack.
So there's no, it doesn't example where there's no continuum to it.
To me, that would be at least a start. But every example that I know without a continuum has a. Yes, and this may not be. It could be that. Yeah.
But you mentioned this a couple of times, right? That one application is when the RR fluxes are present. So can you describe, maybe it's a bit outside what you had planned, but can you describe what is the issue with the RR flux treating up the traditional worldsheet framework and how is it fixed by?
So in string field theory, I know like how to like can be dealt with. In a traditional way, actually, I have never tried to
No,
like.
but I mean, in order to fix the problem, it's better to know what the problem is. That's what I don't know. Whenever is doing things perturbatively, then is there an issue doing RR fluxes perturbatively?
In the string field theory?
In ordinary worldsheet theory.
In ordinary worldsheet theory, I mean, okay, I think what people say, it's not even clear how you like even approach this problem.
So maybe Aditi's question is what's the problem with just exponentiating the lattice? I take the
Okay.
let's say I take a RR vertex operator.
And then
It's smaller than
the problem will be, I mean, okay, so when you try to do, so you have this picture changing operators, I think. And when you are inserting on the worldsheet, there will be like, I mean, you would not know how to like deal with that.
So, but if you do perturbation in that deformation, then you can do.
no, but yeah, if you kind of fix our particles. But as he says, if you choose any particular picture for this vertex operator, then you conclude that almost all amplitudes are zero. Right? Because the sum of pictures has to add up to something. And you exponentiate, maybe it can for one. Right. But what for? So that sounds wrong. It somehow sounds like you are inserting in all pictures. You know, the way we do string perturbation theory is that we choose the picture for it to be non-zero. But how do you do that exponentially? That was one problem.
And how does string field theory help with that?
So in string field theory, I mean, we, okay, so we will see, probably I will.
You will talk about that.
I will try to, maybe in the last lecture, I will try to talk about that. But basically, I mean, you see, here you can handle, I mean, this RF, I mean, this picture changing operator, etc. I mean, there's a very systematic way to like deal with this and prove them in the formalism.
But it's the basic point that there, what we do is work out the Lagrangian as an expansion around the zero RR. Like effectively, like if you compute S matrices up to some number of vertices, then you can reconstruct the Lagrangian and then work with that Lagrangian. So is that basically the point? That base CFT will not have the RR.
Right.
But how do I compute things in a non-trivial RR background?
So say I compute in a flat space, I compute with one scattering, two scattering, three scatterings of RR bits. Okay, that has the data to reproduce my.
But in perturbation deformation, right?
Yeah. So I don't think it can be done. Can be done beyond perturbation in the strength of the RR.
Oh, beyond
No, but that worldsheet thing we can also do that, right? In the in perturbation in fixed.
no, but I think
It's a
you will see, you will soon encounter divergence.
You will need to bend he will be able to bend the theory. Because you know the Lagrangian. You start with the Lagrangian, then you get a delta Lagrangian, then you resolve that delta. That's the different worldsheet theory.
And even in string field theory, so there was this paper by Z in last summer. So there also, I mean, they did up to like say 1 by R to the some R square R cube R4 this up to that order. But beyond that, is still, I mean, there are some obstruction. I mean, they mentioned and so on. So it's still
So
like
you want to treat that in perturbation,
Yes.
you need this plane.
Okay, after this motivation, my I mean, main goal is we want to develop a like offshore formulation for like strings. Okay. And so how we are going to do that? So first, as I was saying, you have this BRST cohomology at the in the first quantized this framework, where physical states are given by this QB V equal to 0, where V is defined only modulo exact BRST exact states. And since there are an infinite number of states, this is a huge amount of redundancy. But if we are just working on shell, then okay, we can just work with equivalence classes, and okay, it's fine. The problem arises if we want to construct an off-shell theory. Then just working with quotients is not an option, and we need a space. Suppose you want to do some quantum field theory, then you need a space which can be used to write an action measure, and we should be able to do perturbation theory. And moreover, we require a framework which can handle this infinite amount of gauge redundancy which is present in the system option. And this Batalin Vilkovisky formalism is designed to handle precisely these kind of systems. So what I'm going to do is I'm going to spend significant amount of time, a significant fraction of time in developing how do we handle this kind of system which have a very arbitrary amount of degeneracy, infinite amount of degeneracy, and so on. So this is a brief outline of my talk. So to develop this VB formalism, what I will do is first I will consider the standard some gauge theory, Young-Mills theory, and what lessons we can learn from there. And then I shall describe I shall consider as generic gauge system and describe what are the possible gauge structures available. I mean, gauge, what is the structure of this set of all possible gauge transformation. And then we shall describe this VB formalism, and then we shall consider the string field. Let's see how far we can go. Yes.
This is for this talk or
No. Let's see. Okay, yes.
So is it possible to find such formalism
Yeah.
in the quantum field theory where I don't want to renormalize the mass, but I want to sort of get
Yeah. So this BB formalism is it's a quantum field QFT technique, and it has nothing to do with string theory. So in fact, for all these 1, 2, 3, I'm not going to even mention strings. I mean, it will just be quantum field theory. I'm just going to consider quantum field theory. But once you have a good understanding of BB formalism, then it's a very trivial step to apply it to string theory. I mean, string theory is so powerful, so rich that it automatically has every ingredient which is required by BB formalism. So the main thing is to understand this framework, and then we can very easily apply it. Yes.
So it's saying that where we cannot apply for quantization of this just
Right.
phase,
Yes.
then we can.
No. So yeah. I mean, of course. I mean, so this BB formalism you can apply even in the standard case when Faddeev-Popov method work, but it will also work when Faddeev-Popov does not work. So we are okay. We are going to consider. I mean, when Faddeev-Popov will work and when it does not work. Okay. So let's see what we can.
Excuse me.
Hello.
I
Yes.
have a doubt. You said that in the worldsheet formalism, writing the loop level amplitude itself is difficult.
Mhm. I mean,
Is that resolved
the-
in
yeah.
string theory?
Mhm.
In string field theory, is that issue resolved?
Yes, I mean, so we can write down, so we can give, so what is resolved is, we know, I mean, how to handle these divergences. So string field theory, so basically in the standard framework, you have a single integral, which is given by integration over the moduli space. In string field theory, what we will do is we will decompose that whole integration into different contributions. Just like, for example, if you're considering, say, if you are say computing the 4-point amplitude in say pi4 theory, then you have there will be a contribution which comes from just the interaction vortex cross diagram, and then you have the exchange diagrams, say 3 exchange diagram. So you can decompose 4-point contribution in these 4 type of diagrams. So we will do precisely the same thing in string field theory. So in that sense, I mean, it is more well defined.
Okay.
So let's see. I mean,
One general question. So, in the end, once you've learned all your lessons, can you package the answer into some effective worldsheet integral or
Effective worksheet is what do you mean exactly?
like some contour or something, you know, some so that if you're using this to cure the problems of the worldsheet, once you've learnt the lessons, can we in the end be doing some slightly modified worldsheet or it's just totally
It's okay. So this again, I mean, goes back to so in the cases where this contour method has been like applied, like for example tree level, then I mean, okay, it is fine. But how exactly even you like so in principle the claim is that this contour method can be like, used to define a like well-defined moduli space integration up to all group order. But even that, okay, that does not tell us about questions like this, say vacuum shift.
Yeah.
And
Right.
so on. So even though you can define you can have a well-defined this moduli space integration, it will not help us understanding like non-trivial backgrounds and so on. Okay, so to properly understand.
So that your final thing is that worldsheet was actually just classical string.
Classical.
I mean, in some cases it works very beyond. But conceptually, worldsheet gives us no more than the classical theory, and then you have to quantize. That's roughly what you're saying, right? Bit disappointing. That's true.
I mean, certainly. I mean, of course, we have like some workable, like.
But hopefully there's something in the end that will.
I mean, yeah, I mean, of course, I mean, we don't understand everything what is string theory, so maybe I mean, a lot has to be. So okay, so.
So just
yes.
one comment about what was saying before about the reduction in states, right? So this kind of thing that Rafiq is talking about, right? Where you look at this full non-perturbative inner product. Yeah, could that not be invoked to kind of argue that the state of space actually less than what the classical string theory is?
Indeed. I mean, it would be so fantastic if. It's one calculation.
Yeah, so probably I mean it's a bit difficult to do, right? This calculation, but some topological strings or something that can because things simplify there.
Yeah, exactly. Oh, exactly. So in a BPS, that's it. Yeah, let's say we can we do localization in the bulk? Okay, localization in the bulk for string field theory and get the stringy exclusion. So that would give us in principle that we have information.
Sorry, this was a big sign comment.
So let's dive into this. So let's first recall some basic features of this BRST quantization of gauge theory. So just let me know when to start.
We are very relaxed.
Okay. So let's consider this Young-Mills gauge theory, okay, which are described by some this Lie algebra. Okay, T alpha are your generators, C are your structure constants. And what we have to do to quantize this system is we consider this path integral over the field.
One question.
Yes.
T alpha is the generator of the gauge transform.
Yeah, I mean the Lie group.
Suppose this gauge, this Lie algebra doesn't close itself. How do you quantize?
Yeah. So this is what is in all these lectures are about.
Oh, I see.
Yeah. Okay. So so we need to evaluate this quantity. Where L classical is your famous, say, Young-Mills action. But this is problematic due to this gauge invariance. The naive path integral does not make sense. It will give you divergent region. And the correct procedure is to count the gauge equivalent configuration only once. Okay. And a convenient way to achieve this was found by Fadil and Popov. So suppose you have some gauge fixing, say you introduce some gauge fixing function, say g of A alpha. It could be your say del mu A mu, Lorentz gauge. And so what you do is you insert the identity operator, okay, this delta g, and this determinant comes because of the change of variable. And you can insert this in the path integral, and okay, you can do integration over alpha, divide by the volume of the gauge group. and okay, you end up with this kind of expression. Okay. So here LGF is the gauge fixing term, and it is responsible for breaking the gauge invariant. And the integration over this lambda enforces this gauge fixing condition. And this determinant factor usually we can like represent as integration over the Grassmann variable to have this kind of like form. Okay? So this is your final like answer.
Basic, how do we get LGF?
LGF. Yeah. So basically, I mean, what you do is okay. So okay, I have skipped a lot of steps here, but what you do is instead of considering this G, what you consider is some G minus F. Okay, in the you insert because and then you integrate over this variable F. Maybe I can write down here.
This auxiliary.
Sorry. Yeah.
If.
Yeah. So basically, what you do is you have maybe I might not remember everything. So maybe what you can do is yeah, suppose you insert something like some square kind of like term, and then you have also have delta of this G minus F. This you can represent as again an integration over G of I G minus F and lambda. Okay, and then you perform integration over this F variable. And then you will get to that. Okay, so you have this final answer, and so this G ghost GH is the like ghost contribution, which depends on CC bar. GF is your gauge fixing term, and L classical is your original like action. So for Young-Mills theory, this effective Lagrangian is given by an expression of this form. So the last term is the ghost term, these are gauge fixing term, and then you have this L class. And this action, you can check that this is no longer gauge invariant, and it is well suited for like doing path integration. But it turns out that this action has not completely forgotten its history of gauging. This gauge fixed action has a global fermionic symmetry, which depends upon the original gauge like invariant. So that is the remnant of your gauge symmetry in this gauge fixed like action. And so this gauge fixed action is invariant under this transformation, which are the our BRST transformation. So suppose you change all the fields involved by like this in this manner. So for example, let's consider one term. So this you have this gauge field A mu A mu goes to it is changed by this eta times delta A mu A, where delta A mu A is given by this d mu of C bar A, and eta is a Grossman odd like some parameter. So if you make this transformation, then you can show that your this gauge fixed action is invariant. And there is a convenient way to like write this transformation. You can write it in this way by introducing this curly operator T with this delta A and del Y. It's just a bookkeeping device, but it's useful. So the invariance under BRST transformation can be written in this form. So if you like apply this operator D on your gauge fixed action, then you should get 0. And moreover, you can check that this operator D is meaningful. So this BRST symmetry turns out to be more useful for the more complicated theory than the original this gauge invariance. And for this reason, we take this BRST symmetry more seriously, and we try to develop a formalism in which BRST symmetry plays an important role from the beginning. So we forget about this original gauge invariant, but we just deal with the BRST, like, and we develop a formalism where we are dealing with just this BRST invariance.
So BRST symmetry does not give rise to divergence.
Which divergence?
Initially, there was a divergence due to gauge symmetry,
Yeah.
but now gauge symmetry is not there. But
Yeah. So yeah, this is just a symmetry, and so I mean, of course. So what I think what you want to ask is whether you will get divergence when you try to do path integration.
Yeah.
Yeah. So in the like for example, now you can do like suppose for example you want to compute the say propagator. If you were using the original, like say expression for path integral, you would get divergent. But now for this, with this like action, you will not get that. To develop this formalism where we give BRST symmetry much more importance, it is more instructive to continue our discussion of this Faddeev-Popov method and derive.
Sorry, that's about the question. There were the gate symmetries were parameterized by functions of space time. This BRST symmetry has the number of parameters in it will be some finite. Will be the number of global gauge transforms. What was the function of space time has become the C field.
C.
So, then that's just normal symmetry, it's not gates. Global.
Yeah.
C of X is will be C of X, right? The parameter.
No, but C of X is a dynamical.
Yeah, but the parameter of the BRST symmetry is also C of X.
Eta.
This what we have.
Eta of X.
Eta.
Yeah.
So just
Just- Yeah.
yeah.
So let's continue our discussion of this Faddeev-Popov quantization and derive the consequence of this BRST symmetry on the correlation function. So let's see how useful this BRST symmetry is. Okay, and this consequence of BRST invariance is expressed by Bott identity, which for Yang-Mills series are called Slavno-Taylor identity, and Jean-Justin equation when applied to this particular BRST invariance. So this is best done by making use of effective action. So I will just state some basic facts. So the generating function, as you all know, it is for Feynman diagrams is given by this path integral. So what we do is we introduce sources, this J of X, and we do path integration. So Z of J is defined by this expression. And suppose you could perform this exactly, you could write it e to the power IW. So Z of J generates all Feynman diagrams, connected as well as disconnected, and W generates the connected diagram. So in particular, suppose you wanted to compute the endpoint function, connected endpoint function, then you just take derivative of functional derivative of W with respect to these sources. And one important object is this one-point function, which is given by single like functional derivative of W. But typically this vacuum expectation value. So this basically this one-point function represents, as we were discussing earlier, it represents the one-point function, and typically it vanishes unless they are part of background. But a more interesting quantity is this vacuum expectation value of the field in the presence of source, delta W by delta J, which, okay, let's denote this by pi without this zero, the vacuum. So treating this equation as differential equation, we can formally write it in this way. So W of J is given by this integral over this expectation value of phi times J and gamma. Gamma is an integration constant and it does not depend upon the source J. This equation defines this so-called quantum effective action. So this gamma is called quantum effective action, and using this relation, we find a simple identity. If you take derivative of gamma with respect to this phi, expectation value of phi, then it is simply the source minus J.
Gamma is the Legendre transform of W.
Yeah, yes, it's a Legendre transform. So in the absence of
Pi sub J.
yes, so in the absence of the source, this equation will reduce to the equation of motion for the expectation value of the quantum fields. And another useful fact about effective action is that it is the generating function for the 1PI diagram. And with 1PI diagram, you only need to do the tree level QFT. Okay? That will give you the full quantum corrected gain function. But the more important point from the point of view of BRST symmetry is that the symmetry of the original like classical action, they may not be the symmetry of this effective action. But instead, this effective action satisfies some non-trivial equations due to the symmetry, original symmetry. So just to see this, suppose our theory is invariant under this kind of symmetry transformation. So suppose you change your field phi I to phi I plus some epsilon fi, okay, where fi have some functions of phi and epsilon is some infinitesimal parameter. And since this is a symmetry of the theory, the classical action and the measure must be invariant. Okay, under this. So S of phi I plus epsilon fi should be equal to S of fi, and if there are no anomaly, then the measure should be invariant. And now we demand that the generating functional Z of Ji should also remain invariant under this symmetry. So the transformed generating functional will be this. So the first line denotes the transformed generating functional. So you have this transformed measure d of phi I prime, then e to the power I s phi prime, and then ddx phi prime times j. But s and d phi prime are invariant. So you just have d phi e to the power is, but phi I prime, which is coupled to source, is gives so that gives you an extra piece. So
why
that
do we expect this to be this promise question? Why do we expect this to be invariant, and why not only after j going to j prime also?
j going to j prime. So we don't want to change the source.
What you mean by phi? Okay, no, sorry, go ahead. It's symmetric.
Yeah. So if you expand this to say first order in epsilon and demand this invariance of the measure z of ji, then basically you have this expression. So basically it's expectation value of this fi. So you have basically integration over this expectation value of fi, this symmetric transformation function multiplied by this ji. Okay. And these are known as Slavno-Taylor identities, and they put a constant on the expectation value of the symmetry transformations. Okay.
Is this equivalent to just word identities of?
Yeah, I mean these are word identities.
So, we often say word identities in terms of del mu, j mu, and that kind of thing.
Right. I mean, if you apply it to like QED, then you will get right.
So this is the same content as
Yeah.
and the fact that you've done it in the presence of j
Yes.
means that this is an all orders kind of thing. Right? So,
Yes.
so that it's actually a word identity on all correlations. Okay. I see.
So using the relation between source, so we had this relation. This J could be written as del gamma by delta of this expectation value of phi. So that using that you can write this Slavno-Taylor identity in this form: expectation value of phi del gamma by del phi. And from this, it's also easy to see why the symmetries of the original action and effective action may not be same. Gamma was your quantum effective action. So if you consider this, so we have this identity, the expectation value of fi multiplied by just
a word identity would be L dot j times phi. It's equal to change expectation value of change in first phi plus change in second. The change in phi is this f. So it would be the word, and then if you integrate the left hand side of the word identity over all the space because it's a total derivative, which it would be you just get 0. So then you get change plus change is equal to 0. Is that the same as the statement?
I think, yeah.
Can you roughly see that it's
okay, so
Why should a conserved current, sorry, what are you identifying as conserved current in this?
I thought it's integral, and so that gets
so I'm not deriving conserved current right now. I'm just deriving the consequence. I mean, how does this BRST invariant shows up in the correlation format, basically?
Yeah. But just because something that's familiar is how, given any symmetry, you get a word identity.
Yes.
So it must be the same thing somehow.
Yeah, I guess it is kind of.
Yeah.
Yeah, I mean,
F would be j to
F is the change.
Change.
So,
Yeah.
delta, the way I'm writing the word identity is delta phi 1, phi 2, phi 3, phi 4,
Yeah.
plus phi 1, delta phi 2, phi 2, phi 4, and so on. Okay, so the F is that delta.
Yeah.
And I just wanted to see that full symmetrization.
yeah, I think probably what we will have to do is, okay, so
What symmetrization?
Meaning that you get, if you have 4 phi's,
Yeah.
then it's delta of the first and second, third, fourth.
But then we have derivative. Then
Partition, not any insert.
you have a derivative which will hit all the phi's in the gamma.
There is no phi.
yeah, I mean here, I mean it's just
presence of J.
J. So basically, I mean, okay, that quantity is basically this quantity.
So I mean maybe because you're in the presence of J now, if you differentiate that with respect to J times,
Yes, then you will get
and
that.
this is J equals 0. You should get what I'm saying, right?
Yes. So you have to insert this extra
Yeah.
phi.
I mean, so you have to take
Derivatives.
derivative.
And Abhi, did you understand how that works? Sorry. I mean,
Yeah, I think, okay, I have also never tried to like see that way, but I think you have to take some derivative. So this derivative, when you take the derivative with respect to j, it will hit this term as well as this term, and okay.
something will happen, yeah.
So if you like consider this quantum effective, so because of like this identity, if you consider this gamma in the presence of like okay, with this change, suppose you change this expectation value of phi I by this amount epsilon times the expectation value of f, then due to this like Slavno-Taylor identity, your quantum effective action remains invariant. So what it basically shows is that this effective action is symmetric under this transformation, not the original like transformation. So quantum effective action remains invariant under if you change the this expectation value of phi by this amount, not the this
Not the field itself.
not the field transformation.
And expectation value of phi. So in the sorry, I just wanted to understand. So suppose I give you a quantum effective action. What do I have to do to check that it's a very what is this expectation value of phi? You solve for
Yeah.
what do you sorry.
So basically, I mean, this is the quantum. So basically, so this is your this phi. This is expectation value.
Yes.
And so basically, you just if you know in principle the quantum effective action, then you can check.
Yes, I want to understand how. So I'm trying to understand what that expectation value is. Say, since a quantum effective action, after you have a quantum effective action, you just do classical physics, right?
Yes.
So what's the difference between phi and expectation value of phi from the point of view of quantum effective action?
So maybe
So just did you go back to your equation on the quantum effective action?
this one. This one, yeah. So
No, so you had an equation saying change
this
that.
this yes.
So suppose I told you that the quantum effective action was I gave you the form.
Yeah, okay.
What
Then
do I
you
have to
could
check?
No, but you just like substitute.
Substitute. And then
substitute
expectation value means nothing then? Or means something? How, what is expectation value?
Oh, this is the quantum corrected field. This is one point function basically.
But if I have the quantum effective action,
Yes.
that is supposed to give me the full answer. Right? When you classical physics.
Yeah.
What you would have written down, I think, was that this expectation value would be inside that fy expectation value of phi. That's what one would guess naively, right? If you do the same exact thing on the effective action, you would just treat the expectation value as the field,
Yeah.
right? And
Yeah.
then you would check the invariance under the first, not quite the first equation, but rather where the bracket is hitting the phi inside f.
But is there a difference between that when we
Here, right?
Yeah, I mean, for example, yeah,
The
this.
last line here, phi square expectation value is not the same.
Oh, you're saying what we have to do is to write the quantum effective action for phi and phi square and phi.
I mean,
You can't. This quantum effective action then is not just the Legendre transform of what you started, because otherwise quantum effective action doesn't know about phi square.
I mean, so yeah, for example, if you had this quadratic, suppose you were changing phi by this amount, then of course this one point function due to like this like
I understand what you're saying conceptually. I'm just trying to say, suppose I have, so sorry, it's very stupid.
yeah,
Suppose you gave me the generating function with respect to j phi, okay, and I Legendre transform that. That gives me a quantum effective action as a function only of phi. There's no phi square in that. Now, how do
so now
check
what
that?
I'm doing is I'm changing the action. I'm changing the field by this amount. So this is something I'm doing externally.
No, but I give you the quantum effective action.
Yes.
So function only of phi. Now, how do I check that it's invariant?
So you change the phi, right? So it's still a function of like phi, right?
So function of phi.
Phi.
Then I can change phi by anything and check if it's invariant.
Yes.
But I don't understand what now the difference between expectation value of phi squared.
Yeah.
You mean like this statement?
Yeah, how would you check that? So you are saying it should be invariant under this, right?
This
phi,
one, yes.
yeah.
Yeah.
But what is that second bracket?
This expectation of
That
phi
thing is
square.
not there in the action at all to begin
Yeah, but in principle you can compute in QFT, right?
You can, but it's not a constraint on the quantum effective action because that doesn't know what phi square is. It is a constraint of quantum effective action if you enlarge your notion of quantum effective action to be action with respect to all operators.
How is that defined?
You can Legendre transform with respect to each operator. There are not a source for each operator.
Oh,
And the Legendre transform with respect to each.
Yes.
is that
If
what?
that's what you're doing,
Yeah, so okay, this one let me think. Mm. So you cannot so for example, suppose you try to compute this expectation value of pi square in the original, like even before introducing the this is effective action. So in that formalism, this is well defined, right? I mean, you can still compute.
So you compute mod pi square in terms of exponential value pi square in terms of expectation value pi and put it there.
that's effectively like turning on a source for pi square.
Yeah. So we are going to turn on sources for this pi square, etc.
But I'm just saying that this does not seem like a. Suppose I gave you Legendre transform of J phi. That is the quantity we started talking about. Is that constrained by this condition? Or you need a bigger object?
So okay, maybe can you make your question more? I mean again.
Okay, let me say. You compute J in expectation value with J phi.
Yes.
Okay? Then you Legendre transform.
Yes.
That quantity is a function only of phi.
Mhm.
In expectation value pi.
Yeah.
Only of expectation value of phi. Okay? That is what sometimes we call effective action. If you're going to try to check that it's invariant under this other bigger thing, then that is checking not the effective action, but some other bigger object.
So basically, your question is how we compute like this quantity. Right?
We can compute it.
Yeah.
But it's not, we need just knowing the effective action as a function of phi is not enough to do it.
This will not be invariant because this right hand side doesn't appear. This pi square doesn't even appear.
Right?
It can be the zero source value, like you introduce
Zero source value of what?
pi square. Like take the object you're talking about, derive it with respect to the source pi square, set the source to zero, and that can be the secret.
Okay, so then you need the quantum effective action as a function of phi and phi square.
Why? You're only modifying the expectation value pi, not pi square. You just need the value of expectation value pi square.
But how do you know the value if you just have phi?
You can compute the thing you said and then derive it with the source and then set the source to zero.
So you need some external information. You need more than the effective action.
Of course.
So you cannot just check that the effective action is invariant. Because if you just I give you the effective
Of course,
action and ask
yeah.
you, is it invariant under this? You cannot answer that question.
To find the symmetry operation, you need that information, but you are checking the invariance of the effective action under this method.
But you need to know what that right hand side pi square was, and that is not contained in this effective action. You need to do a separate calculation to find what that is.
Of course. Yeah.
So it's very different from if I give you a classical action and I want to check that it's invariant under something. I don't need any information outside the classical action. It's just there. It feels to me like what you're saying is that what the right object to deal with is effective action of every operator in the effective action of pi square, pi cube, so on. Then you can by these equations check the
symmetry. That's why I mean these are very strong constants. Yes.
very strong, but of very unusual quantity.
No, but so given the effective action, this effective action, so just the gamma of excitation pi, I can convert that into a W of K. I just use that to compute pi square expectation value. Right? I don't need any extra.
No, I don't think so. Because you're computing these at separated points. Meaning that W of J has information only of correlation functions of phi. Now you want correlation functions to some other operator. Now maybe what you're saying is that in the bootstrap way you will get it all. But it's a very complicated thing.
But you are saying the problem is with having them set on top. The problem is with computing correction to them.
Yeah, because you get anomalous dimensions and so on, right? All that information is done.
Also, he's telling us what not to do here.
What?
He's telling us what not to do.
He's saying that what not to do, but it would be useful if it was a statement of, yeah, you give me the effective action, I tell you what to do to check that it's valid.
Which is his next slide.
Yeah. But
Which is the next slide, let's
no, probably not.
That was the integral equation, right? Not this.
Yeah. You mean this one?
Yeah.
I mean, so basically, it's like I think what you are saying is like correct. It's a very strong constraint on effective action. It has information
It's
from.
based on a very strong effective action. And the kind of thing you don't normally compute.
I thought this stuff was a constraint on the effective action, right? Not
Sorry?
the normal. This stuff is a constraint on the normal effective action, right?
Yeah, this gamma, yes.
No, but this same issue, right?
How do you?
Um,
Same thing.
but this normal effective action also satisfies like this constraint.
But this is where the question is, right? What is the meaning of this? This is five.
So that you have, yeah, I mean, okay.
It's like you have a function of x that you are
So
checking what
basically,
happens if x goes to x plus
So
one.
we have a precise definition of this. Like fi is nothing but I mean you define it by the original like path integration of the.
It's completely well defined. Yeah. But like, if you want to think of it as a constraint on an effective action, there is a quantity you can do. You take every local operator in the theory and Legendre transform with respect to each of these and compute an effective action with respect to each of these. That is some humongous object, and then this is the constraint on that. But it's not a quantity we'll ever know. But okay, maybe it's already.
Yeah, it's fun. I mean, okay, we'll see. I mean, how I mean why.
Sorry, but what is the okay?
Uh, so okay, let me go ahead and maybe it will clear. Okay, let's see. So this linear. So from this argument, we can also see that the linear symmetry transformation of the original action will automatically be the symmetry transformation of the effective. Yes.
Oh, we have no, you're telling.
Oh, acha.
We have to leave it for?
430. Okay. The BRST transformations are not the linear symmetry transformation. So the effective.
Sorry, I mean the first point is what Shiraz was arguing.
No. So that is the linear like symmetry transformation. So linear symmetry transformation will be like symmetry transformation of the original as well as the effective action.
Because then phi square and phi are.
Yeah, same. But the BRST transformations are not the linear symmetry transformation. So the effective action will not be invariant under BRST like transformation.
So you're trying to say precisely because of the issue she has raised, you need something more complicated.
Yes.
That's what you mean.
So to see what are the consequences of this BRST invariance, I mean, okay, we have already introduced all the like techniques. So what we will do is we will introduce sources for the BRST transformation, as you were saying. So so we had this BRST transformation of the field written in this way. So delta of phi I was eta times d of phi I, and let me denote this d of phi I by this bi.
Why is that not linear?
Sorry?
Linear, right?
No. I mean, not for every field. So, for example, you can see. Yeah. Yeah. Here, for example, here it's not linear. So, and we consider this modified action. So, we introduce source ki for these BRST transformations bi. Okay. And this action will be invariant under like because of d square being 0. So d of this modified action is 0. And this function ki are the sources for BRST transformation. And one thing you can notice, this bi and ki will have opposite Grassmann nature compared to this original field phi I. I mean, this we can see from here because eta is Grassmann odd. So suppose phi is Grassmann even, then bi must be Grassmann odd.
And will it stop here or will have to do more and more?
No, so d square is 0.
Right?
Because d square is 0.
But now when you take the change in these guys,
So I'm not going to consider the other like this thing, but d square is 0
d
here.
square is 0. No, so it's BRST close.
Yeah, yes.
But now you will, I would have thought that you would now try to find the transformation of this d phi.
D
Of a, right? Sorry, of eta times bi.
Yeah.
That's it, because d square is 0.
I now take the quantum effective action of this, and I would have thought that this will also be changed. No, you're saying k doesn't change. It doesn't change.
Yeah, k.
Even quantum mechanics.
Yeah, k is just the source. It's just some function.
No, not this b.
Bi. Yeah, I mean there is no like further transformation because of d square being 0.
So b does not change under the transform. I see.
So
Okay, fine. So just chance. Thank you.
Okay, so in the presence of this BRST sources, the generating functional, we define this to be the so this will be the new generating functional. So we have the original source Ji, phi I Ji, and then we have included this term Bi Ki. And since the fields and sources can be Grassmann odd, the ordering of field in this expression is important. And by convention, we have put these sources Ji and Ki.
So effectively now, in terms of this new field of Vi, you linearize the transformation. If we write down this, the new transformation, is it now linear effectively in the and therefore now it's now the old form.
But I mean, okay. So the main thing which we are after is okay. So first, this vacuum expectation value of the phi I in the presence of okay, this both Ji and Ki will be given by okay, it's the same expression. But okay, so this delta R represents the fact that we are taking derivative from the right because the fields could be Grassmann odd. So if we are taking from the there will be some plus minus. But then these signs become important as we go along. And this relation, as before, we can use it to express Ji as a function of this Ki and this phi I, expectation value of phi I. And taking this into account, the effective action will more precisely be written in this form, where now you have to include this Ki, now the equations. And using this, okay, again, you can derive these two useful identities, this delta L gamma by delta of this phi I equal to minus Ji and delta R of gamma by delta of Ki equal to this Bi. So this is a useful exercise to derive. You can try. And now if we recall this general Slaughter-Taylor identity, general word identity, which was Fi-Ji. So for BRST transformation, Fi is Bi. And this Ji was this del gamma by delta phi I. So basically the constraint is this equation. It's a constraint upon the effective action, which is imposed by BRST symmetry, and this is known as Ginger's. So we can introduce this bracket.
So this is like a mixed quantity. So it's a mixed quantity because you make effective action for phi, but you still have sources for transformation.
Yes.
So it's neither an effective action nor a W. It's mixed.
So in fact, the formal
position variable and K can be thought of as momentum.
No.
So
K is a source
K
for
is
the
the
source.
so I'm talking in the Lagrangian description, this I can be thought of as a position.
You're saying that because it's a transformation,
Oh, you
it's a
mean
canonical domain.
Canonical.
That's
the way you have written down this.
yeah, that probably you can give an interpretation.
Interesting.
So because later we will see. I mean, this will have a symplectic structure. So okay.
Sorry, can you do the other way around, Kumar?
Yeah.
Sorry, just because of symmetry, is there an equation where you do this derivative of gamma with respect to J and there with respect to B?
Derivative of gamma with respect to J.
There with respect to B.
J and B.
Right, a quantum effective action of B, but not fit.
Yeah, what would that mean? Is that a meaningful thing?
Not sure.
That would be phi.
Yeah.
And that would be
Hmm.
K phi.
Yeah.
Probably not.
Yeah, probably.
This symmetry problem.
Hmm.
Oh, because the phi B is on the right hand side, I guess. Yeah. Okay, sorry.
So what we can do is we can define this bracket so where you have this delta R. So suppose you have two general functions f and g, then okay, you define this bracket. Then this identity which we had, which is the constant on effective action due to this BRST invariance, can be written in a very compact way that this bracket vanishes, gamma gamma equal to 0. So in terms of this bracket, it's a very compact expression.
Wait, the fact that it's not identically 0 is some Grassmann square.
What is not identically?
If I put an F and G equal,
Oh,
gamma,
yeah.
it looks like it's just identically
0. No, only for gamma it will. I mean, for gamma you can show that okay. I mean, this is 0. You can write it in.
No, I think he's asking
No,
about
so-
the bracket, noting that phi and K have opposite Grassmann region.
Yes.
That would give you a plus sign.
Plus, yeah.
It's opposite Grassman nature, then it will have.
Yes,
yes.
Same
Yeah, yeah.
Grassman nature, then it will have.
Yeah. So, I mean, for example, suppose, because gamma is Grassmann even, if it were Grassmann odd, then it will be 0. So, this bracket is known as anti-bracket, and the sources for BRST transformation Ki are known as anti-fields. Okay. So, what we will do is we will exploit these ideas of anti-bracket and anti-fields to develop the BV formalism. And that can be, so I mean, this was just in the context of normal like BRST invariance in normal Yang-Mills theory. But then, okay, we are going to generalize these like notions of anti-fields and this bracket, and that will give us this BB formalism. So BB formalism is basically this exact. So what we do is we introduce sources for all sort of like symmetry transformations, okay? And this is what we will do. Maybe. So okay, we will introduce. I mean, okay. So there will be ghost field, there will be anti-fields, there will be anti-ghost field, everything. So we will see what there. So
But it's finite structure, just ends at this. It's not like you need codes for codes for codes.
Oh, we will need.
Even in this gauge theory, you need this kind of thing.
Yes. I mean,
Why?
this is what we are going to now.
No, where is it here?
Oh, here it is not. I mean, here, I mean, it was just a
Want to complicate life.
Yeah, it's so it was just in the context of normal Yang-Mills theory. I mean, this is what one can do.
But in normal Yang-Mills theory,
Yes.
will we ever need codes for codes?
No. So I mean, maybe I don't know if we can continue, but
Oh,
but maybe next we can. So what we are going to discuss is what are the possible general gauge structures are there. Okay, so there we will see. I mean, why we need ghost for ghost and so on.
in string theory.
In string theory and normal in general also.
In normal Yang-Mills theory, we
No, not in
Where do we need it? Yeah, where do we need it?
So this you will need. Suppose you are doing say P-form fields. For example. So suppose you are doing P-form field, then you will have gauge invariance for gauge invariance and
But
so
why
on.
does it stop? It will stop, right?
For P-form field, it will stop at some level.
So is there any normal structure for which it doesn't stop?
String theory.
But string theory, okay. Fine.
Yeah.
So because it has infinitely many fields.
Sorry.
It
Yeah.
has infinitely many fields.
Infinitely many
Infinitely
fields.
gauges.
That's non-compact gauge.
Non-compact. Yeah, I mean, so yeah, general. I mean, some structure can be there. Of course, I don't think.
Non-compact gauge should self.
I don't.
Yes.
Why?
I don't know.
Not.
Yes, I'm sure.
No, I'm not sure. I mean, only example. I mean, I know like which is well studied is string theory. I mean, where you really need all this.
That's because Ashok has worked in string.
High spin gravity also has this kind of structure.
High spin gravity will have will need both. It will terminate that.
N equal to Fourier angles is also normal angles in your.
Yeah.
It's very.
More normal.
No, but it will have higher form gauge speeds, right?
Sorry.
It will have higher form gauge speeds.
High form gauge fields.
You mean in the field?
No, which high form gauge?
Like maybe I'm wrong. Sorry. Just Amy, you are saying.
Cillian theory may have.
Auxiliary theory.
Our.
Yes. We'll have.
Basilia means batteries.
Not every investigate.
I think there you have infinite like things. So probably.
String theory with more gauge speeds.
Maybe Basilia theory is the real formalism because it's lots of auxiliary fields. Basilia theory, half part of Basilia theory was to get the physical content out of it. So somehow maybe it can be thought of as the result of all of this. That would be certain. It's the same gauge.
No, but this is our point.
Right? So
It's the same gauge method that we're dealing with. Interior.
It's
it's the higher form stream. Higher form. Yeah. I mean, the gate invariance that makes has been public, masters has been public.
But how do you say, like, why do you say it's directly related to what you're doing in the
I don't know. It was a big comment, but you know, you need some gate symmetry to make, if you have a 5 symmetric index field, you want to make it gauge invariant, you need something to get rid of its negative norms. So there's a lot of gate symmetry in this. Okay? And
But
maybe
in that theory, it does want to work with quantum action, quantum effective action.
actually, even just
But is it Basilio
Maybe.
quantized using vivid formalism? Okay, I'm not
but
saying.
it's not quantized. Basically. Yeah, so it's classical.
It's not quantized.
I've never seen anything about quantized.
So that means it is already quantum.
Yeah, maybe somehow it is the
I mean, this we are saying this feature is for the quantum action, right? Quantum effective action that you have more and more forces and so on.
No, not to, I
No,
mean,
because
not,
that's how
this
we-
was just a motivation. I mean, how, but we are going to, I mean, use this similar set of ideas now, but it will be for general action. only.
That's
We
good.
will define three
what
kinds. of-
Vasily came upon was this structure
Yeah.
somehow because he needs to do a lot of stuff to get the physical inverse space from
Yeah.
what he has.
But I was thinking that this structure was quantum structure.
Yeah, I know.
Yeah,
So
but that's
Vasily was
not
classical.
Was-
Apparently.
I mean, they don't, to what extent do they know the classical action of the sleep in the
But what is the
When I last
difficulty?
10 years ago, they didn't do it.
But what is the difficulty in quantizing?
What's the classical action?
Yeah, to start with, there's no action. Very, very good.
Oh,
so maybe-
Some action,
Okay.
just two questions.
But it's dual theory.
Its dual theory is almost free. Yeah.
Yeah.
It's very well known. So it's a kind of situation where duality is almost useless. Because you know the field theory, you have a claim for the dual, but you can do the calculations only in the field. Alright.
Seems like.
Well,
We hope.
you have it.
Okay.